All right, today we're going to talk about simulations. And simulations are really the only thing we haven't talked about yet from the first section of the chapter. And they are about estimating probabilities and using some random process to simulate an event that we're interested in the probability of. For those of you, the analogy I used yesterday is that for those of you who may play like D&D or are familiar with that, you do simulations all the time in D&D. You roll dice, and getting above a certain number corresponds to succeeding at the event. This would be like a skill check for those of you familiar. Getting above that would be considered a success, and getting below that, you would fail the task. And that is the basic idea of a simulation. We're using random numbers to correspond with particular events based on the chance of the thing happening. So the first thing we're going to simulate is the NLCS, or a league championship series in sports. So an NLCS, you don't have these notes, by the way, so you'll need to get some of this written down. There won't be a lot to write down today. So you can just get out some paper and title it simulations and write down the examples as we go. And we're going to use both the random number table out of our book and the random INT out of our calculator. So if we have the NLCS, like a lot of sports series, it is best 4 out of 7. And so that means that 7 games aren't always played. It is sometimes however many games we need for one team to get to 4 games. So another way to say it is that the first team to 4 wins. So let's say that Team A has a 60% chance to win a single game. Oh, I can't write this morning. A single game. And so we're talking about their chances of winning a single game, not the whole series. Just because they have a 60% chance to win one game doesn't mean they have a 60% chance to win a best 4 out of 7. Those are different probabilities. And so as we start to run these simulations, you might start to think about whether you think the probability is higher or lower than 60%. That might be a good exercise. This is a hard probability to actually calculate because you need to think about that we're not just calculating winning 4 games out of 7, because they could win and sweep the first 4 games, or they could win the first 4 out of 5, or they could win the first 4 out of 6. It doesn't always have to go to game 7. So we're going to simulate this. I'll show the calculator first, but we're going to do the same idea for a random number table. So using the digits 0 through 9. And what we're going to do is we're going to simulate this 60% chance to win a game. We're going to simulate this 60% chance of the thing happening. The way that we're going to do that is that we're going to have 6 out of these 10 digits represent a win, and 4 out of the 10 represent a loss. So that means if the digit is 0 through 5, 0, 1, 2, 3, 4, 5, that's 6 digits. 0 through 5 is going to represent a win, and 6 through 9 is going to represent a loss. So if the digit's between 0 and 5, then we say that they have win. If the digit's between 6 and 9, then we say that they have lost. We repeat this until one team has won 4 games. So either A wins 4 or A loses 4. So again, what we're doing here is we're using numbers. We're using random numbers to kind of model or simulate the event that's happening. In this case, we're using the digit to represent a game, a baseball game. And so we're going to go to the calculator. I'm going to start by doing this on the calculator. And we're going to use something that we have already used in the past, which is random int. So we are going to go to find random int. Remember, you're going to go into math. You're going to go into the math menu. And then we're going to scroll over to probability. So math over to probability. And then number 5 is random int. So we're going to go down to number 5. That's random int. And for you guys, it's going to bring up a menu. It's going to be really similar to normal CDF, where you do a lower bound and an upper bound. And then instead of median standard deviation, you're going to put n. How many random numbers do we need? So we're going to go, our lowest number is going to be 0. Our highest number is going to be 9. And n is going to be 7, because our games are out of 7. But as soon as one team wins 4 games, then we can stop. So here is my group of random numbers. Yours might be different from mine. But here is our, we'll keep track of wins, winning the series and losing the series. We have, remember, 6 through 9 is a loss, so this is a loss. This is a loss. We've lost the first 2 games. But then here comes the comeback. 0 through 5 is a win, 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 and they win the series in 6 games. Let's do it again. We have a loss, but then our next 2 games are a win, But then here comes the comeback again, loss, 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 and they lose the series. Next group. I'll tally this one more time. We have a loss, we have a win, we have a loss, loss, win, win, loss. And so in theory, what we would do here's loss, win, 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 and we win that one. So in theory, what we would do is we would gather several different trials of this, simulate this event happening over and over and over, and get an estimate based on that of the probability. Right now, they've won the series 2 out of 4 times. So we'd estimate a probability of even 50%. But in theory, what we would want to do is a whole bunch of trials of this. So we'd want like 100 or 1,000 runs of this series to get an estimate of how many times out of those 100 did they end up winning the series. Questions on that first one? We'll do a couple more examples with this. So the idea here, you don't need to write this down, but I just want to highlight a couple things. We're repeating a single event. We're using numbers to model the outcomes. And then we should talk about how the trial is going to happen. And in that case, the thing that we do is that we stop after 4 games or 1. And then we're measuring who was the first team to get to 4 games. That team won the series. And then we're going to do it hundreds of times, get the results, and get my conclusion of what the probability is. All right. Let's do another example. And I'd like to give you a few minutes to think about, you don't have to use the digits 0 through 9 here. So I want you to take about 2 minutes to think about what is the probability that you want to simulate, and how many times do we need to do the thing that we're trying to do? What digits are we going to use to represent what? So I'll give you about 2 minutes to think about that. And so that's the thing that we're trying to think, is that remarkable? Could that have occurred just by chance? So probability of 10 correct out of 20. If they have a 1/3 chance of guessing correctly. Well, if they have 1/3 of them out of 20, then our overall expectation, you should have a guess as to the overall expectation of how many we should expect them to get correct out of 20. Probably about 1/3 of the 20. But what's the probability of guessing? Let's put at least, so that we're not having some kind of exact estimate here. And so now we're going to move on to what digits we're using to simulate this probability. We can do it that way. It doesn't matter which digits you use as correct or incorrect. The thing that matters is that 1 out of your 3 should be correct and 2 out of your 3 should be incorrect. So you could use 1 and 2 to be incorrect and 3 to be your correct. But as long as a third of your digits are correct and 2/3 of your digits are incorrect, then it should work fine for you. And we're going to do this 20 times. And we're going to answer, did she guess at least 10? Because that's what we're asking, is how remarkable is this? So we're keeping track of how many were correct out of the 10. So that's what we're going to use random INT to do. So we're going to go on random INT again. So we're going to go to math. We're going to go over to probability. And then 5 for random INT. This time we're just going to go from 1 to 3. So lower is 1, upper is 3. Our N, how many of them do we want? This time we want 20 of them. So any ones mean that we got them correct. So we're counting up. I see, how many ones do I see? I see 1, 2, 3, 4, 5, 6, 7, 8. So that is 8 out of 20, correct? That's not 10. And again, the idea is that we would do this a whole bunch more times. 1, 2, 3, 4, 5, 6, 7. Not at least 10. 1, 2, 3, 4, 5, 6. Not at least 10. And then I would keep going along this line. There's 8. And keeping track of how many we're getting correct. 1, 2, 3, 4, 5, 6, 7, 8. And so it doesn't seem like we're getting at least 10 correct a lot. But that doesn't mean that it's impossible. It is possible. So eventually, with enough times through this simulation, we'll get a certain amount of them getting 10 or more correct. In fact, if you did this on your calculator, you may have run into a time where the person got at least 10 correct. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There it is. There's a time where we got at least 10 correct. And so we've done this. So far, our running probability is that out of 1, 2, 3, 4, 5, 6. So we've done this 6 times and we've gotten it once. And the actual answer for the probability, is about 0.091. So about a 9% chance of getting at least 10 by chance. And so if you did this 100 times, you would expect about 9 or 10 times out of the 100, we would get successes here. So to recap again, and then we'll do one more. We are using these random numbers to estimate a probability. And we are simulating a trial of a certain amount. In this case, it was guessing our 20 cards. So each of those numbers represented a card and guessing a card. And we either guessed correctly or incorrectly. And we're wondering, did we get at least 10 of them correct? That's what we were looking at. All right. I'm going to give you a minute to read the next one. So write down the key bits of information here. I'll give you about a minute to read it. And then I'm going to divide you up into groups and have you discuss how we're going to do this. Last time we used the numbers 1 through 3. What digits do we want to use this time? What numbers represent what? What does each number, each of the digits represents something? Last time it represented a card. Last time it represented a baseball game. What is it representing this time? How many times are we running the trial? What are we finding the probability of? So what we're going to do here is we want the digits 1 through 19 to be student government. 20 through 150 is going to be everyone else. And we're going to repeat this process 10 times for our 10 good spots. And we want the probability that at least 5 of the spots go to student government just by chance of the lottery. How likely is this to have occurred by chance? So each of the numbers is going to stand for a parking spot this time. And we're interested in 10 of the parking spots. So I'm going to go in math over to probability. And I want 5 random INT. This time we want 1 to 150. And we want to choose 10 of them. So 1, 150, 10. And then we're going to hit enter, and then we're not going to hit any other buttons. If you scroll up to highlight it or you try and type in something else, then it's not going to scroll in the way that you want it to. And so now that we're here, we can count up how many of the spots, remember 1 through 19 is the spots going to student government. So there's a 17, there's a 12, there's an 8. So only 3 of the spots went to student government. I'm going to hit enter again to get another trial. This time, that's 22. That's not low enough. This time, only 1 person in student government got the spot, 13. Same thing here. Only 1 of them got the spot. There's 1. There's 2. Only 2 people got the spot. The probability that at least 5 of them will get the spot, the actual answer here is actually lower than our last answer. Our answer here is about 0.004. Less than 1/2 of a 1% chance that 5 of the spots went to student government out of the 10. So that might be enough to indeed suspect some shenanigans are happening.